Okie doke. So let's carry on. So this is now lecture 5. We've gone through quite a large range of topics so far. After building up the more structural aspects of the standard model, we're now deep in the nitty-gritty, looking at the various sectors and their interactions, and the way that those interactions, for instance, the electroweak interactions, differentiate between chiralities of fields. And in particular, we saw in the last lecture, we looked at the electroweak interactions of the leptons. And we saw that QED emerges out of SU2 cross U1 breaking in a very natural way. And we recovered the couplings to the photons that we expect. The neutrino was neutral, does not couple to the photon, whereas the leptons like the electron, muon, and tau lepton all have charge plus or minus 1. On the other hand, we saw that the charged current, the W bosons, connect neutrinos to charged leptons, as one would expect. And furthermore, the neutral current, the Z boson, has a piece that couples equally to left and right-handed leptons, but also has another part that's dependent on the chirality and differentiates between left and right-handed fields. And this is something that has been confirmed in experiment, and there are many ways to confirm this. I think possibly one of the cleanest is by looking at things like left-right asymmetries in Z decays. Okay, so that was the leptons in the gauge sector. Of course, lurking behind all of this was the Higgs, because it was really the Higgs that gave mass to the W and Z boson in the first place and created that spontaneous symmetry breaking. But now we want to go and think a little bit about the Higgs and leptons and what there is to say there. And we will see that it's a fairly vanilla story. There's not a tremendous amount going on with the Higgs and leptons, apart from when we think, for instance, about neutrinos and neutrino masses, which we will get to at the end of this lecture, or maybe 2/3 of the way through. In the middle, I will just do a little bit of a back of the envelope calculation to give you a sense of how Higgs physics and leptons connects to, for instance, the LHC. I'm very near to CERN at the minute, and the LHC is nearby underground, so it's very relevant. And it's also very relevant for our field for the next 18 or so years while the high luminosity phase of the LHC is running. And so we will calculate decay width using the things that we've learned that falls neatly into the ballpark of where we're going with high luminosity LHC. Okay, so the leptons and the Higgs, that's the title today, I hope you can read it. So the lepton-Yukawa interactions are of the following form. I call it LL. We have the sum over the Yukawas, IJ. With what I would call EC, often referred to as the right-handed leptons, I, and then LJ. So big L here so EC had hypercharge 1, and L had hypercharge, -1, and L had hypercharge 1/2, and was in an SU2 doublet. And the H also is in an SU2 doublet with hypercharge 1/2, so they're dotted together. And then usually plus Hermitian conjugate, just to make the whole action Hermitian. Okay, now as we saw before, we can perform, as we did with the quarks, for instance, a couple of lectures ago, we can perform a unitary rotation in flavor indices of this guy and this guy to completely diagonalize this matrix here. If we also had a neutrino, a right-handed neutrino matrix, then we wouldn't have been able to perform that diagonalization for the neutrinos, just in the same way that we couldn't perform that diagonalization for the down-type quarks. And we will come to that in the next lecture, or maybe if we're lucky at the end of this lecture. So we can perform these unitary rotations. We rotate these flavor indices by a 3x3 unitary matrix, and these flavor indices by a different 3x3 unitary matrix to bring this into a completely diagonal form. In which case this becomes a much simpler Lagrangian. It looks like YE, ECE for the electrons. That's the electron Yukawa, because it's now diagonal. We can split up the 3 generations and name them electron, muon, and tau. Coupled to the Higgs plus Y mu, EC, mu, L, mu Higgs, where mu is not a Lorentz index. This is just the name associated with the muon. Y tau, EC tau, L tau, and H. Where, for instance, in here, what I'm calling LE is a doublet that contains mu E, and let's call it EE. Should be the because it's in the doublet, we would call it the left-handed or the weak eigenstates. Okay, now recall that in unitary gauge, so we can always do this last, it's the same one each time. So you do this last gauge transformation all at once across the whole standard model, but we can always do it for the gauge bosons to eat the Goldstone bosons to become the longitudinal components of the gauge fields, in which case we don't see the Goldstone bosons anywhere in the action. This is the choice of unitary gauge. We can always choose a gauge. And in unitary gauge, once again, I'm sure you're bored of me saying this, big H just becomes 0 and then V plus H over square root of 2, where H is the Higgs boson, the mass eigenstate that's been discovered at the LHC, and V is the vacuum expectation value of the Higgs field. So V is something like 246 GeV if we're in natural units, and we've said H bar to 1, and that means that V over 2 is about 174 GeV. Okay, so we can do this, and then in the electroweak broken vacuum, we get that LL now becomes something like V plus H over square root of 2, and then we get Y E E C E E E, where this would be the right-handed component and left-handed, plus Y mu E mu C E mu plus Y tau E tau C E tau. Different notebook, different textbooks will use different conventions for notation, but this is all equivalent. So you may see, subscripts with L to mean left-handed or right-handed, or projection operators if it's working in 4-component Dirac notation. It's like music. There's only so many notes on the stave, but somehow there are a seemingly infinite number of ways to put them together. So different textbooks have different notations, but it all means the same sort of thing. Okay, so what do we see here? We see that because we only had one set of Yukawa interactions, we've only generated one set of masses. This thing has not generated any neutrino masses whatsoever. And furthermore, just as in our toy example, we did this, if you recall, this toy example of a spontaneously broken U1 symmetry. And when we did that spontaneously broken U1 symmetry, the mass of the fermion, if the scalar phi was coupled to the fermion, had a Yukawa interaction with the fermion, it was, the Yukawa coupling times F, where F was the vacuum expectation value divided by square root of 2. And we get the same sort of thing here. So the electron mass will be YeV over square root of 2. And so that we can see that these are pretty small numbers, right? The charged lepton masses. So for example, the electron mass, which is something that we measure, is 511 keV. But that is, YeV over root 2. So that's something like, YE. So that's something like YE times 174 GeV. So the electron mass is the electron Yukawa is a very, very small number. And we discussed this before in the context of approximate symmetries of the Standard Model. There is an approximate chiral symmetry for electrons at high energies just because this Yukawa happens, which is the only parameter that breaks the chiral symmetry, happens to be very, very small. And it's of order 511 keV, so times 10 to the minus 6 over something like 174. So this is a number that's in the ballpark of 10 to the minus 6. The muon mass, so let me just erase that and write down the masses. So ME is 511 keV. Mu is 105 MeV. Rounding to some number of significant digits. And M tau is 1.8 GeV. So you see that these are all small Yukawa couplings, even for the tau lepton. To get down to 1.8 from 174, you're talking about 10 to the minus 2 or so. For the muon, there's another factor of 10, so you're talking like 10 to the minus 3 or so. And just the electron, another 2 orders of magnitude. Okay, so the leptons, for the most part, couple pretty weakly to the Higgs. And this really is a huge puzzle. You know, when we wonder about the structure of the Standard Model, something we do spend a lot of time scratching our heads about is why, number one, why there's a pattern, you know, across the quarks and leptons, there are these patterns, but also how these numbers can be so small. They are really, it really smells like whatever the microscopic completion of the Standard Model is, the sort of the next ultimate theory from which we can derive the Standard Model. It smells like there's something going on there, right? There's a pattern. I think you'd have to be fairly insane not to acknowledge that there's a pattern in the quark and lepton masses and Yukawa coupling, and consequently the Yukawa couplings. Yet we don't know where it comes from. And also this is pointing towards completely different physics. And it's something that we don't, I think, acknowledge quite enough, which is until we had discovered the Higgs, we were only really experimentally aware of forces in nature that were of a gauge form. General relativity, so gravity, is a type of gauge theory. So the diffeomorphism invariance, the fact that you can change how you parameterize your coordinate systems in gravity, is a gauge invariance. And that diffeomorphism invariance absolutely puts the way that things can interact with gravity in a straitjacket. And we saw that also with the gauge symmetries. You know, with the U1 gauge symmetry, all the interactions have to be essentially through some form of covariant derivative. All the interactions with the gauge fields, that is. And there was the arbitrariness of a choice of charge. When we go to non-abelian, there's not even a notion of charge. So there's very little arbitrariness at all. There's the representations. You can choose higher dimension representations, but that's it. And the gauge coupling is absolutely fixed. So you have the same strength of interaction everywhere. And there's not even this ambiguity of charge for non-abelian symmetries. And up until we discovered the Higgs, all of the forces that we had discovered in nature were of this form. They were all gauge forces. So there was really only one paradigm that was at least experimentally confirmed. There was really only one paradigm for fundamental forces. Of course, there are other sorts of forces that we've observed in nature that are not fundamental, you know, that they are sort of collective phenomena that might arise, you know, in laboratory experiments and things like this. But in terms of fundamental forces, it was really just the gauge paradigm. After discovering the Higgs, we've now discovered the fact that there are experimentally confirmed the fact that there are different types of forces beyond the gauge paradigm. And that's really a very, very profound thing. We take it for granted because this model has been sitting around for decades. And although it's only been confirmed experimentally now, in some of the aspects, not all of them, although it's only been confirmed experimentally now, we've sort of had it in the back of our minds because we learn it in courses like this course, and take it for granted that when the Higgs was discovered, that this sort of confirmed it. But in fact, this is an entirely new paradigm where there's now experimental evidence for an apparently fundamental force carrier that has absolutely nothing to do with gauge forces. And that links entirely to this puzzle of the masses and the Yukawa couplings. There's no sort of quantization, so no notion of quantization of Yukawa couplings. These Yukawa couplings are completely unrelated to gauge couplings or anything like that. There's no straitjacket for them to be in. They could essentially be arbitrarily different numbers. And this creates an enormous puzzle, right? Why these Yukawas? You know, what is behind? What's the mechanism behind generating them? What's the origin of non-gauge forces? Is it some physics beyond the Standard Model that looks totally different to what we're normally used to? It's not really clear. So although I presented this in a rather prosaic manner, I think it's important to keep in mind that these things that we're now exploring at the LHC and hopefully at future collectors are really a new frontier, not just in terms of confirming the standard model, but they're really a new frontier in terms of the physical paradigms that underlie our understanding of forces in nature. Okay, so after that, we'll get back to more prosaic things. Let's do something very prosaic. Let's do a little example. I think that these sorts of occasionally little examples of how to calculate or how to estimate certain things can be useful. So let's think about leptons in Higgs physics. So as I said, the mu on Yukawa, for instance, is a number which in natural units, we're talking about 10 to the minus 3. And so that's pretty small. And it is a very rational question to ask, well, could we just go out and measure that? You say, right, this is the model, this is a model, it's a hypothesis, a scientific hypothesis. Say we want to say, okay, well, let's go and actually just measure this and see what the answer is. What do you need to do? And the first place to look is obviously the LHC, because at the LHC we can create Higgs bosons, so that's a great start. So one can ask, how much integrated luminosity at the LHC would you need to discover the fact that the Higgs couples to muons through a Yukawa coupling like this? To confirm it, of course, the hypothesis is working well, we know that, but we really want to confirm it. Hypotheses are always hypotheses, and the experiments are extremely important in making sure that we're on the right track. We can't just keep piling guesses upon theoretical guesses upon theoretical guesses without at some point checking them. And so it's good to check it. So how do we check this at the LHC? Well, I'll give you some numbers. So we want to see how much integrated luminosity do we need to see to observe a single Higgs to mu plus mu minus event. And I'm going to assume there's no background. There is background, and we'll come to that in a second, but let's just assume there isn't any at the minute. Well, the production cross-section to make a single Higgs boson, this is a complicated calculation, at 13 TeV is of order 50 picobarns. And I can tell you that the branching ratio, we can calculate the branching ratio to tau leptons, which is actually also sort of being measured at the moment, which is a remarkable thing. The branching ratio to tau leptons is there's an error in my notes here, 0.066 to tau plus tau minus. Say BRH, the tau plus tau minus is something like 0.066. Okay. Now we know that the decay of the Higgs to a pair of fermions is going to scale, the amplitude will scale as the Higgs going to some fermions proportional to the Yukawa. We call it Y, like this. So the cross section, can you see that okay? Yeah, I think so. So the cross section, which is proportional to the square of the amplitude, will be proportional to the Yukawa squared. So then we can take this branching ratio and multiply it by y mu squared over y tau squared to get the branching ratio to muons. So we can extract the branching ratio to muons just straight away from the branching ratio to taus, essentially, up to subleading corrections. And we know that the number of events is just the luminosity times the cross section. That's how many times something happens. So we assume the total cross section to decay to muons is the cross section to produce a Higgs times the branching ratio. Once you've produced it, the branching ratio for that Higgs to decay into muons. If that's the total cross section, we just need to multiply that by the luminosity to get the number of Higgs to mu decay events. And so n mu plus mu minus will be something like the integrated luminosity times 50 picobarns times y mu over y tau all squared times 0.066. And we can invert this, so we want this number to be 1, so we have a single event, We convert this to get the integrated luminosity that's required. Now we just put in the numbers. Y mu over y tau is simply m mu over m tau because they both have the same factor of the Higgs vacuum expectation value. So we just invert this and we get that L for one event is something like 100 inverse picobars. However, at the LHC, we will actually have something like 3000 inverse femtobars. So at the high Lumi, that's at high Lumi, LHC, we will actually get something like n mu plus mu minus Higgs decays is something like 30,000, 30 times 10 to the 3 events. Which is really amazing. Now, if we didn't have any background, the statistical uncertainty would then go something like the square root of the number of events. So we would have, it's like 10 to the minus 4, so we would have a statistical uncertainty that's even below the percent level. So we would be able to say, well, to an uncertainty of less than a percent ish, that we can confirm at the high luminosity LHC that the Higgs boson decays to pairs of muons. And that's good because if you want to see something at like 2 sigma, which would be 95% confidence, then we would easily satisfy that threshold. However, it's not quite so simple because in actual fact, when we look at what would we do experimentally, we would look at pairs of muons and we would want to see, is there a bump at around 125 GeV where the Higgs mass is? And those pairs of muons, they can be produced in loads of different ways, right? You can have QQ bar through a Z boson to pairs of muons, QQ bar through a photon to pairs of muons, and many other processes that might involve other jets in the final state that get lost down the beam height and so on. So in practice, one has a steeply falling background of muons. It looks like this if we look at the sort of the event rate. If we were to bin events as a function of the m mu plus mu minus, the invariant mass of the muons, then it would look like this. And what we would hope to see at 125 GeV would be a little bump that corresponds to the Higgs part. So that, because there's also background in the process, we don't get to use the full background-free statistical significance. Instead, you have something like signal over root background, so it gets hurt a bit. But nonetheless, we can observe, start to observe Higgs decays to muons at the high luminosity LHC, which is no mean feat because it would really be starting to confirm Higgs decays to second generation leptons, and would be probing this model, the standard model, down deeper into deeper corners of coupling strength, down to very, very small couplings. What excites me about it is that this Yukawa interaction here is something like 10 to the minus 3. This is an extremely small, extremely weak interaction. And so just at a very basic level, I find it very, very exciting that one could potentially probe such small couplings that are in the Higgs sector. It took decades and decades to even produce a Higgs and confirm that it's there. It was not an easy task, and it required thousands and thousands and thousands of people over many decades working towards that goal. Yet by the end of the high luminosity LHC, we would be able to say things like, well, we can start to probe couplings in the Higgs sector that are of order 10 to the minus 3. Okay, so to wrap up leptons, let's now go on to discuss neutrinos very briefly. I find this also to be a very intriguing part of the story for the Higgs. And also, I think, as I mentioned before, it smells like there's something funny going on with leptons, which is really differentiating them from quarks. They're not just like an uncolored version of quarks in a certain sense that I will define a bit more clearly now. So neutrinos and Higgs. So in the absence of a right-handed neutrino, so if we don't have, so remember we had for the quarks, we had the Q doublet, and then we had UC and DC. So we had, and we call them often the right-handed quarks. But for the leptons, we had the lepton doublet and then just EC. We had no NC, which would be like the same thing as UC for the quarks. And because of that, we have no right-handed neutrinos. If we did, there would be completely gauge neutral. The thing to couple in there would be completely gauge neutral. So within the Standard Model itself, as stated, there was no way of writing down at dimension 4 or below an interaction that would generate neutrino masses. However, as I mentioned before, there is an interaction for which this can occur. It's known often as the Weinberg operator, which is this dimension 5 interaction that we've mentioned, where we have something like L dot, I think it was H dagger. And we have, let me put a little epsilon, H dagger squared over, let's call it lambda L, where this has mass. It's not a mass scale, as you're probably tired of me saying, but it has mass dimension 1. And what is this epsilon here? This epsilon tensor is something that I've actually glossed over a little bit in the previous sections. It's just the antisymmetric tensor, something like this, in a certain basis. And it means it's one special property of SU2. So these are L and H are doublets of SU2. One special property of SU2 is that we call it pseudo-real. And the reason for that, sorry, that's not the special property. The name isn't the special property. It has a special property, and because of that special property, we call the symmetry pseudo-real. And the reason for that is that this epsilon tensor can take two fundamentals, so two things that transform, like you multiply on a unitary 2x2 matrix, and form a combination of them, which is actually invariant under SU2. So normally you would have to have a fundamental and an anti-fundamental. The notation would be something like a 2 dot done with a 2 bar. And then in here you would get a U dagger, and in here you would get a U, and U dagger U is the identity, and that's how you get singlets. And that's sort of what we've been doing until now. But there's an additional thing you can do, which is actually you can form a singlet just for SU2, where you, well, only for SU2 if we're working with a 2-index antisymmetric tensor. You do IJ, and then you can have a 2I, 2J, summed over the epsilon IJ. And if you do an SU2 unitary transformation, it turns out that this object here is also invariant. So that's why we can write down this invariant here. For more for larger index gauge groups like SUN, you can do a similar thing involving an antisymmetric tensor with n indices, but we won't encounter any situation where we need to use that. Okay, so this means that we can use H and H dagger to form things that transform like a fundamental under SU2. Okay, so we can write down this term. And when we write down this term, we can see that contracting these things together, that L dot H dagger is L dot epsilon dot H dagger. So I'll just put the epsilon in here and forget about this term. Which would give us something like neutrino EC, and then 0 minus 1, 1, 0, and then 0 V plus H over root 2. And we can multiply all this together, and we get EC in the top, and then minus mu in the bottom. And contracted on here, the thing in the top just contracts to 0. This is in unitary gauge again. And the nu, we will get something like V plus H over root 2 times mu. So then this thing squared nu squared, you can see that this thing here generates something that's quadratic in nu in the left-handed neutrino field, which is a Majorana mass, essentially. This gives a mass to the neutrino. And so this Majorana mass, we can calculate from this, the Majorana mass, the neutrino mass. So this is not like the other masses. So the other masses that we've encountered so far have paired a left-handed field with a right-handed field. And in terms of spinors, four component spinors, you can write that as a Dirac mass. And as I said before, it preserves some form of chiral symmetry where you can rotate things with opposite phases. Here, this is a completely different beast. This is just, and the neutrinos are the only electromagnetically neutral fermions that you could do this with. It's after electroweak symmetry breaking, so it comes from an operator involving the Higgs, but nonetheless at low energies below the electroweak symmetry breaking scale, this is a gauge. Nu squared is a gauge invariant operator. And so we can write just for neutrinos, because they're special and just at dimension 5, not at dimension 4 below, we can write an operator that will generate a mass, which scales like v squared, where v is the vacuum expectation value of the Higgs, over lambda L. And so if lambda L were around something like, I'm doing this causing in my head, so I might get this wrong, if this were something like 10 to the 13 GeV, then the neutrino masses would come out around something like 0.3 electron volts. This is in natural units. So we have some very intriguing hint going on here. And it's a hint that has kept many theorists busy for a long time. And it's a potential hint towards a very, very high energy scale in physics, because the neutrino masses are all around, the sum of them has to be less than about an electron volt. There are various ways of putting that together. You can look at the mass differences that we measure from atmospheric and solar neutrinos, for instance. And combine that with the fact that cosmology requires, because these neutrinos, the cosmology is all very calculable. We know how they interact. We saw yesterday they interact with the Z boson and the W boson. So in the early universe, they will have been produced and they will move about. And if they move about too much, because they're relativistic, they're super light, they move about too much, they have a noticeable impact on structure formation in the universe. And so cosmology sets limits on how much they can be moving about, and that actually puts limits on how heavy they can be. And so you get a limit that's around, that the sum of the neutrino masses has to be around like at most an EV or something like this. I don't have the exact number to hand. And this means that the heaviest one is probably around something like 0.3 EV. So this is known as the Weinberg operator, and this is a way in which it appears the neutrinos are, the lepton sector is being treated completely differently from the quark sector. And that's because in the absence of QCD, it's possible to have operators like this at dimension 5, which are not too low, but that in particular violate lepton number and can generate Majorana neutrino masses. I should note, I've been a stickler for this and I will always be a stickler for this. If you analyze in that old H-bar counting way that I mentioned, the scale in here, this has the dimensions of a mass scale divided by a coupling. So in fact, in any theory which generates this interaction, if there's some microscopic theory that leads to this, it can involve things you may have heard of or may not have heard of, like the seesaw mechanism and so on. In any theory that generates it, there'll actually be a coupling up here and a mass scale down here. And this means then, coupling squared and a mass scale down here. And what this means is that if this coupling were super duper small, you could generate 10 to the 13, even if m were lower. So 10 to the 13 GeV is not, it's sort of a it's sort of the scale that we need in terms of lambda L, but it's not necessarily the scale we require in terms of the mass scale. This operator could be generated for very much smaller masses if there's a small coupling in the theory. And that's also equally plausible. That's reasonably plausible because these interactions have to violate lepton number in some way. So it's plausible that the violation of lepton number is somehow suppressed. Okay, so this is one of the puzzles, and I had planned to put this at the end of the lectures and treat it in its own right, but this seems a natural position at which to discuss this aspect of neutrino physics. All right. Now let's go on. We have time to discuss quarks. So we've done leptons, and now we're going to discuss quarks in the Standard Model and their interactions with the Higgs. And also in terms of the lecture week gauge interactions. I will not be able to finish this material today because we only really have something like 13 minutes left, but may as well make a start. Okay, so for quarks, the story is very different because now we have QCD in the game. And QCD at very high energies, famously, there was a Nobel Prize awarded for this, the gauge coupling becomes very, very small. So you could, QCD on its own, if you don't include the other bits and pieces like hypercharge and SU2 weak and things like this, if you just had some fermions in the fundamentals of SU3 gauge group, and the same number of fermions as in the Standard Model, then we say that that theory is very special because it's UV complete. And what that means is that it can be extrapolated up to arbitrarily high energies and it never breaks down. It in fact goes towards, as you go towards the far UV, so the tiniest distance scales possible, it becomes essentially a free theory. The gauge coupling becomes so weak. Of course, that is little bearing on reality because there's no such thing as arbitrarily high energies as a result of, for instance, quantum gravity. We're going to hit the scale of quantum gravity at some scale and so on. Nonetheless, this property has very profound implications for the Standard Model because if you reverse that and you talk about going to lower energies, well, that means the gauge coupling is becoming stronger and stronger. And so there is a range of energies, you know, when energy, we're talking about energies that are sort of greater than around GeV. We can talk about QCD and quarks in terms of the SU3 gauge interactions. And quarks and gluons that can scatter off each other. We can write Feynman diagrams, we can do stuff like that. But if we were to go to, so I'll say quarks and gluons here. If we were to go to energies below a GeV or so, the quarks and gluons are actually confined. This gauge coupling becomes so strong that it becomes impossible at those energy scales to separate, to pull apart quarks from each other. And there's an analogy which actually sort of works quite well. It's not perfect, which works quite well, which is, you know, if you were to look at a hydrogen atom, and you have the electron, you know, going its orbitals around the proton. Now, if you were to scatter, you know, a photon off that atom at very high energies, above the binding energy of the electron in hydrogen, you could basically forget about the fact that it was bound in the first place. That would be just a minor detail. It would be essentially, you know, if you're talking about GeV or something, the electron would be essentially sat at rest somewhere and you're scattering off it and doesn't care so much about the fact that it's bound in terms of energies to the proton. However, if you were to then scatter light off the hydrogen atom that is very low energy, so very long wavelength that's larger than the atom, you would not be able to ionize the electron. So then it becomes completely important that that there's some binding, that electromagnetism is binding the electron to the proton, and in fact you wouldn't even the light to a large extent wouldn't even see the existence of the atom. The atom would be essentially neutral, and the best you could hope to measure is maybe some dipole moments, because if if it's in some excited state, then the wave function may not be completely spherically symmetric and things like this. That's a good picture in mind to have for the quarks and gluons as well. You know, at very high energies, we can talk about quarks and gluons and they're not bound and we can scatter them off each other without really worrying about what goes on at, say, a GeV where we're scattering them at, you know, a TeV or something like this. It's an irrelevant question, almost. Not in terms of the process of actually getting them to scatter, where it becomes an extremely relevant question. But in terms of the microscopic physics, the details of their interactions. But as we go to lower energies, they bind together, and then the picture that treats them as independent quantities just doesn't really work. And so below a GeV, we will come to this in the second last lecture, perhaps, or maybe the last lecture, hopefully. Doesn't really make sense to talk about quarks and gluons. It makes sense to talk about things like pi mesons and rho mesons and protons and neutrons and k mesons and things like this. All of the bound states of quarks and gluons, which is sort of like the atomic physics of QCD. The analogy doesn't go, it's not a robust analogy, but as a first pass, it's sort of useful. Okay, so throughout what I'm discussing here, I'm really only ever talking about a description which is appropriate, just the correct effective description above the QCD scale. So when we do this, in the standard model, the Lagrangian is the following. The sum over all of the kinetic terms, so that's something like I, Q dagger, J, this is the doublet, D slash, this is the covariant derivative. Q plus I, U, C, dagger, J, D slash, U, C, J, plus I, D, C, dagger, J, D slash. This is an unfortunate use of D's, DC, plus the sum over Yukawa couplings. So now we've got IJ, and we've got the uptype Yukawa couplings, IJ, H dot QI dot UJC, plus, if you recall, we tried to do a diagonalization of all of the Yukawa matrices before, and because we have the same Q entering here, I'm sorry, I'll finish this up, lambda IJ D. Sorry, I'll discuss this a bit more accurately in a second. Q J I DCJ. So in here, we have UCJ and DCJ there, but we have the same QI in here and in here, but we have two matrices. And if you will recall, about 3 lectures ago, when we tried to diagonalize these matrices, we found we can only diagonalize one of them. There will always be a leftover undiagonalized unitary matrix here, which we call the CKM matrix. And so now we could actually, it's just a question of notation where you do this. If you left the undiagonalized one here or the undiagonalized one here, it makes a little difference. Physically, the descriptions will always be exactly equivalent. But nonetheless, this has very important consequences when we think about the electroweak sector. So here, this thing is diagonalized. Just point this out, diagonal. This thing is diagonal. And this thing is some unitary matrix. And if you recall, that unitary matrix has 3 essentially rotation angles in it and 1 phase. Okay, so we can again go to unitary gauge for the Higgs. And if we recall, so going to unitary gauge, we have that the Higgs goes to, again, V plus H over root 2. And well, now, because we're breaking electroweak symmetry, the components in a doublet get split apart. And so the Q doublet, DL, I'll call it in this case, now there's some discrimination depending on the Yukawa matrices. It's no longer SU2 invariant. So let's first consider the hot quarks. Here, this thing is diagonal, and everything follows through as before. We have this epsilon in here for the down quarks, so we don't need to worry about it here. So V plus H just hits onto the lower component here. So we get that M ij u is equal to v over root 2. And then we have lambda top, lambda charm, and lambda up. And all the other entries are 0. This is the mass matrix. And it's a Dirac mass matrix because we have a left and a right-handed component. We don't have something like UC squared because that would that's forbidden by gauge symmetry. So these are Dirac masses. Okay, so what is there? There are some things that are sort of noteworthy. This side of things is relatively boring compared to what we're about to come to with the down quarks. But there's some noteworthy things. So for instance, the top quark mass is about 174 GeV. And what this means is that, oh, sorry, I have to switch notation from Y to lambda for you Kelvis. I apologize for that, but let's stick with it now. So the top Yukawa, actually no, let's switch back, it's bugging me. Let's call these Y's. Y. Okay, so the top Yukawa coupling YT, this is then an order one-ish quantity in natural units. It's one, essentially almost one. And so that's actually sort of a pretty big coupling. We're used with the leptons used to having small Yukawa couplings. Yet in the top sector, that's not true. It's pretty big, and that means that the top Yukawa will have a pretty big influence on Higgs physics. For instance, loop interactions, so the dimensionless, so these Yukawas have coupling dimension 1. So quantum corrections will involve factors of h bar. So the leading quantum correction will have one factor of h bar. So the leading quantum corrections to anything in the electroweak sector, so the Higgs, for instance, will go that involve the Yukawa, will go like, let's say, correction, one loop. Corrections will go something like h bar lambda top squared. There's usually 4 pi squared that comes along for the ride, and there's also the multiplicity because there are two chiralities. There's the left and right-handed guy, and on top of that, there's also the 3 colors because these things are charged under QCD. So it's something like 6. These corrections go something like 6 times 1 squared over 4 pi squared, which is not small at all. We're used to the alpha electromagnetism, so alpha effective, let's call it, top, the thing that shows up in one loop corrections. It will be something like 6 over 4 pi squared, which is like a half. That'll be the effective number that you start seeing in quantum corrections. Whereas we're used to these quantum corrections being much smaller in electroweak physics. So for instance, alpha electromagnetism is, famously 1 over 137 at low energies. So that means top physics is important for Higgs physics. Furthermore, because the top quark is heavy, it's 174 GeV, it is impossible for the Higgs to decay to a pair of top quarks. And that's the only fermion actually in the Standard Model to which the Higgs cannot decay. And because of this, it ends up having all sorts of interesting features. Furthermore, so that's to do with Higgs decays, but because it has a big coupling, although the Higgs cannot decay to it, it can significantly influence the properties of the Higgs boson. So, for instance, the leading production of a Higgs boson goes through actually a top quark, and it's a quantum production where so Higgs production. The production of the Higgs goes through gluon. This is at the LHC. It depends on what you're colliding, but if you're colliding protons at high energies, to a large extent, that's a quark collider and a gluon collider. And if you're working at very high energies like 13 TeV, then and each of your protons has in the lab frame, it is coming in with 6.5 TeV of energy. Then you just need to ask for a small momentum fraction. The quarks are carrying a big chunk of the momentum of the proton, but not all of it. And if you're only asking for 125 GeV to produce a Higgs, you only need to borrow a small momentum fraction from the components of a proton that are making it up in order to make a Higgs. And so when you go to small momentum fractions, there's loads of gluons that are carrying a bit of the momentum of the proton. And so when you're doing physics at like 100 or 200 GeV at the LHC, gluons are super important. But also for the Higgs, the top is super important, and the top is essentially the window between the QCD and the Higgs, if you think about it, because the top is the colored particle which has the strongest interactions with the Higgs. So anything involving QCD and the Higgs, the top is going to be the main star, and indeed that's the case. So the production of the Higgs boson at the LHC, it actually proceeds through a loop of, unsurprisingly, top quarks, and you produce a Higgs boson like this. This interaction at low energies essentially looks like H over V, which has to be on-dimensional grounds, alpha strong over something like some numerical factor in front of it involving these factors of 3 and 2 and so on, 4 pi squared, and then the 2 gluon field strengths. You get an operator like this, and that's actually by far the dominant production mode at the LHC, and of a Higgs boson. So the top coupling to the Higgs is super important. Similarly, the top decay to the Higgs the Higgs decay to gluons goes through this loop, but also Higgs decays, for instance, to photons also have a big component that is mediated by top quarks, because again, the Higgs is uncharged under electromagnetism. So if it's going to talk to photons, it actually has to somehow pass through some other particle in order to get access to those photons. But again, the particle that has the biggest coupling to the Higgs that is charged is the top. So the top plays an important role. There's also another diagram for Higgs decays. This is Higgs, involving electroweak gauge bosons, which should also not be overlooked. That also couples to photons, so it'd be like W's in here, but also tops. But nonetheless, we see that the actual discovery of the Higgs, which was predominantly through production by gluon fusion and then decay into photons, is actually driven by the top quark. The workforce of Higgs physics at a hadron collider is really the top quark. And so that aspect of Higgs physics regarding the quarks is super relevant and important. And as we stare down the barrel of almost 2 more decades of Higgs physics at the high luminosity LHC, this will continue to be the case. Okay, and I will leave it there, and we will pick up the down quarks and the Higgs sector in the next lecture.